Hello everyone and welcome to MV Tutors. I'm Telo and I'll be looking at chemical equilibrium with you guys. Before we get started, please don't forget to like our videos and also subscribe to our channel. Also, if you'd like to have a private lesson with us, do visit our website to make a booking at www.mvtutors.co.za. Alright, let us get to the lesson. Alright, so if they were to ask you what chemical equilibrium, what would you say? Alright, so it is defined basically as the state at which both the reactants and the products are present in concentrations which have no further tendency to change with time. That is what we call equilibrium. So you have your reactants, you have your products, have their concentrations that will not be changing. Okay, so now we get to some definitions. Okay, something you should be quite familiar with. For example, like what are non-reversible or irreversible reactions? Well, an easy way to demonstrate or rather to say it is if you were to get your ingredients to make cake. Okay, so you have your reactants, which are the ingredients, and the product, which is the cake. Well, basically, you can't then take your cake and get back your ingredients, which are your reactants. So those are the kinds of non-reversible or irreversible reactions. An example that I've showed here is carbon. I've illustrated here when you have solid carbon. So the gas, when it reacts with the carbon, it sort of like eats away the carbon. Okay, and then you have what forms is carbon dioxide gas. So once you have carbon dioxide gas, you can't go back and say, I want that solid carbon as well as the oxygen gas. It just won't happen. So that is a irreversible reaction. Okay, then you have reversible reactions. Okay, for example, if you want to produce ammonia, maybe for fertilizers or whatever. Okay, so you have nitrogen gas as well as hydrogen gas, and it gives you ammonia gas. So even if you have ammonia, through some processes, you can get back your nitrogen and your hydrogen gas. Okay, it's quite possible. And then if we refer to an open system versus a closed system, what exactly are we referring to? Well, basically, if you have an open system, you have your reaction or reactants or products. They're basically continuously reacting with the environment. Okay, and that's not really that great for us at times. Sometimes we desire to have a closed system, which means that your reaction is basically isolated from its surroundings. So whatever will be happening around, it will not affect the reaction, which is what we want. Please guys, when we refer to closed system, we're not saying that you have a box and your reactants are in there and your products are formed and it's just this closed room. No, we're just saying that, whatever's happening in the surroundings, it won't affect your chemical reaction. And that is something that you need to define for each specific reaction that you're busy with. Okay, cool. And then we talk about yield. There are sometimes questions that will be asked pertaining to the yield, asking you, what do you predict the yield to be? Will it be quite good or very bad? Economically, how does that affect, people and so forth? So basically, when we say yield, we're referring to the amount of product formed during a chemical reaction. We just want to know, listen, this product that we want, will it be there? In what amounts, in what quantity? Can we make a profit from it? So you're interested in the product. So whenever they talk yield, think product, okay, during a chemical reaction. And then we get to dynamic chemical equilibrium. That is really our focus here, okay. So what is a dynamic chemical equilibrium? Well, firstly, before we even go far, it is established in a closed system. So you need to understand that your reaction should be in a closed system as we define. It should be isolated from surroundings. The conditions need to be kept constant. All right, that's the first important thing, closed system. And secondly, or basically the rate of your forward reaction will be equal to the rate of your reverse reaction. Okay, so they take place at the same time and at the same rate. And just because we can't see with our naked eye that a reaction is busy occurring, it doesn't mean that it has stopped. Like we said, it's reversible. So it keeps occurring in the background. On a microscopic level, you can see that the reaction is ongoing. But the main thing with dynamic equilibrium is that the rate of the forward reaction takes place at the same rate of the reverse reaction. Okay, the same time, same rate. Okay, so yes, please, they love asking this question. Make sure you understand and you know what dynamic equilibrium is. The rate of the forward reaction is equal to the rate of the reverse reaction, and it is important that this all occurs in a closed system. Okay, now let's talk about the factors that influence the chemical equilibrium position. Okay, because you might be in a state where you have chemical equilibrium and then there's a shift. Something just happens. There you are enjoying your life and then just life happens, and we need to adjust. When life happens, you need to adjust and find a new equilibrium, if I could say. Okay, so yes, what are things that can actually influence the equilibrium position? Okay, temperature, okay, concentration as well as pressure, they really have an influence, and we're going to discuss also when that happens. If you increase temperature or decrease it or increase pressure, what actually will happen? How will the equilibrium shift? Okay, it's nice. It would be nice if we got a manual like that in life, that if this occurred, this is what you must do. But unfortunately, when it comes to life, it depends really who you go to for help. You'll find a way through. But let's focus on chemical equilibrium. Okay, so for you to understand what would happen if you were to change the temperature, the concentration, or the pressure, you have to be familiar with Le Chatelier's principle. He has to be your friend in this case. Okay, so what does Le Chatelier say, or what does the principle say? Well, basically it says when equilibrium in a closed system is disturbed, okay, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. Okay, quite a mouthful, but it's understandable. So for example, there you are, enjoying your life, and then December comes and the festivities and everybody's just eating everything, and you decide to join in and you gain weight. So before that, you were at equilibrium, you were eating healthy, good lifestyle, and then December came and you decided to eat rubbish, and then January came and you were basically the disturbance has been in your weight. Okay, so Le Chatelier says, okay, what is this disturbance that happened? I gained weight, I can't fit into my clothes, I'm starting to get pimples, things are not working out really. So that is the disturbance. So now Le Chatelier says, okay, fine, I want to favor what will happen to oppose that disturbance. Okay, so what would that mean for you? It means let's start eating healthy, drinking a lot of water, exercising, so that we get to a new equilibrium. Okay, and by exercising you gain muscle, so you won't exactly look like you did before. Maybe in your first equilibrium you were skinny, then you gained weight and became fat, but your new equilibrium will be you are toned and you are well developed, and this definition, this muscle. Okay, so basically that is what Le Chatelier's principle is saying. A disturbance came to your equilibrium, but instead of sulking and blaming everybody, we get up, we pull up our socks, and we're like, what is the new equilibrium that will oppose this change that just happened? And then you just do it. Okay, so that is Le Chatelier's principle. So now we're going to talk, what is the effect of temperature? What would happen in a case where you increase the temperature? Now we're referring to the chemical reaction, not anymore to weight. That was just an example. Okay, so if in your chemical equilibrium you were to increase temperature, so you understand, okay, by referring back to our videos on the rates of reaction, when you talked about endothermic and exothermic reactions, you know that endothermic reactions, they require heat, they absorb heat, okay, in order for the reaction to occur. Whereas exothermic reactions, they release heat, okay, so once the reaction has occurred, they release heat off into the system. okay? Whereas endothermic, they absorb, take in, gobble up the heat for the reaction to occur. So when you increase temperature, what would happen? Increase in temperature in the form of heating would favor the reaction that absorbs the heat. So increase in temperature would favor the endothermic reaction. Okay, so that is what happens. And then when you apply Le Chatelier, because the endothermic reaction will be favored, Le Chatelier is like, hey, what happened here? What was the disturbance? Increase in heat. And what happened? The endothermic reaction was favored. Okay, whether endothermic reaction was in the forward or the reverse reaction, that's not really the case here, but you just want to identify where is the endothermic reaction. So by reducing the temperature in the form of cooling, well, that basically will favor the reaction that releases heat. Okay, so therefore it would favor the exothermic reaction. So that is the disturbance. There's cooling, and now if your exothermic reaction is forward or whether it's reverse, doesn't matter, but it will favor the exothermic. So that would be the disturbance. And Le Chatelier pops in and says, hey, how are we going to change this? How are we going to fix this such that we get a new equilibrium? Well, basically, if maybe your exothermic reaction was in the reverse, then Le Chatelier says, let us favor, or let us shift now towards the forward. Okay, I hope I'm making sense. But basically, that's how you would apply a change in temperature. All right. So what would happen if you were to apply a change in concentration? Okay, so when it comes to concentration, the gases and aqueous solutions are applicable. Okay, so with concentration, I would like for you to think about a seesaw. Okay, I don't know if you see here, that is actually an R for reactants. So R is like holding the part of the seesaw there, and then we have P for the products. Okay, so what would happen if you were to increase your reactants? Okay, so you have your person there, the reactant, let's say they gain weight. Okay, so if they gain weight, your equilibrium, well, this would happen to the seesaw, right? You would have your reaction there, you have your product there. Okay, so basically the reactants will be quite heavy. Okay, so you've increased the reactants, right? So where will the which reaction will actually be favored? So by increasing the reactants, that is the disturbance. Le Chatelier comes in and says, let's get a new equilibrium position here. How are we going to do that? Well, we are going to favor the product side, the forward reaction. Okay, so we need to now go this side to go help the products to be like, hey, please gain weight. Please, such that we get back to our equilibrium position or a new one. So it basically would be forward favored in this case. Okay, forward or product favored. Okay, and the same would happen if you were to increase your products as well. Okay, by increasing your products, now your products are heavy. Okay, so the seesaw will go the other way, and you have your reactants on this side. So what will the Chatelier advise? Well, he would tell you, listen, you gotta go help out the reactants there. Okay, so it's gonna be reactant favored or reverse favored. Okay, so that is what you do when you add reactants or when you add products. But what would happen when you decrease the reactants or decrease the products? Okay, so now let's say you decrease the reactants. Now the reactants have lost weight. They haven't gained. Okay, they were so busy and stressed out because of exams and they lost weight. So if they lose weight, the products will become heavier, right? You have your reactants over there, and now we're like, oh, reactants, what happened? Like, I've lost weight. Okay, so we need to go and help the reactants, guys. We need to go help them gain some bit of weight so that we can get back to equilibrium. So when you reduce the concentration of reactants, well, we're gonna go help the reactants out because they've lost out. Okay, so it will be reverse or reactant favored. That is what Le Chatelier says. This is what we must do. Okay, the same as when we also have our products reducing. Okay, so what must happen? Like, maybe for example, you want to produce chocolate. Sorry guys, I love sweet things, so yes, I'm gonna refer to food and weight. So let's say you want to produce chocolate. So if I want to get a lot of chocolate on my product side, okay, I would have to remove. So as it's being produced, I remove it and I keep removing it. And by removing it, I would have to then make more. So let's say I remove the products. Ne? Now it means my reactants are gonna be heavy. Okay? And then we're like, how? The products now have lost weight and they're light. So let us go help them out. Okay? So now it will be forward favored, okay, or product favored. So by removing more chocolates, by removing chocolates, more chocolates will be produced, and I'll be happy if that happens. Okay, more chocolates, more smiles, we're happy. We'll deal with the weight later. But basically, that is what happens. If you're going to remove a reactant or remove a product, Le Chatelier says, okay, we've removed it, guys. Let's go help it out so that it can come back again. Okay, and if you increase the concentration of the reactants or increase the products, well, basically, you will have to apply Le Chatelier by saying, if I have increased the reactants, I also need to go and increase the products. Okay, so we're gonna go and be product favored in such a case. Okay, so I hope that makes sense. It will settle in well once we do an example. Alright, and then we get to pressure. So pressure would apply to gases only. Please don't bother yourself if your chemical reaction just consists of solids and liquids or aqueous solutions. Don't bother talking about pressure. Okay, pressure is applicable for gases. So if you were to increase pressure, okay, when you increase pressure, do you realize that, let's say you have a big volume, okay, and you increase pressure. When you increase pressure, your volume gets constricted. Okay, so by increasing your pressure, you are actually reducing your volume. So what will be favored? Okay, when you are talking about or referring to pressure, you have to look at your equilibrium equation. Okay, so let's say we have our products here. We're talking gases only here. Okay, so let's say we have our products. We have 2A plus B. They're all gases. Okay, and then we get 3AB. It's also a gas. Okay, so here, no, actually no, let's not make it 3AB. I'm gonna make life hard for myself. Let's say we have 2AB. This is just an example. So we have 2AB. Alright, cool. So when we talk about pressure, what we're really interested in when we're looking at our chemical equation, we want to know the amount of moles for the reactants and the amount of moles for the products. So, for example, for our reactant side, we have 2 moles of A and 1 mole of B. So in total, we have actually 3 mole on the reactant side. And then on the product side, we have 2 mole of the product. Okay, so if you increase pressure, which, means that you are decreasing your volume, where will the reaction be favored? In this case, you're going to actually look at the side that has the least amount of moles. So an increase in pressure will favor the side that has the least amount of moles. Okay, so the least amount of moles are favored. Therefore, in this case, the products have the least amount. So this is product favored. Okay, now the opposite also applies. If you were to decrease your pressure, okay, so now there you are, your volume is little, but you had high pressure, and then you release the pressure, and then it starts expanding again. So it means your volume will now increase. Okay, increase in volume, And if you have an increase in volume, okay, if you reduce your pressure, what you're going to look at, the side that has the most amount of moles. So the most amount of moles will be favored. And in this case, it is the reactants. Okay, so this will be reactant favored. And that's basically it. So with temperature, you gotta see, is it exothermic, is it endothermic? Okay, and you apply things as per normal. If you think about concentration, think about a seesaw. Okay, what would happen if you were to increase your reactants or decrease your products or whatever? Okay, so what would happen? Think about the seesaw concept. And with pressure, think about the number of moles. Okay, I would advise you to look at it this way. If you increase pressure, you are reducing volume. Okay, so look at the least. So look at so if volume will be reduced, look at the least amount of moles. Okay, so that's how I would look at it. If the volume is reduced, look at the least amount of moles. If the volume is increased, meaning the pressure is reduced, look at the most amount of moles on your reactant side or product side. And that's how it works. So I've taken here a screenshot from the study guide Mind the Gap, which actually gives you steps to follow. Okay, so when you're trying to predict the change, okay, so where will the equilibrium change in a closed chemical system, all right, in dynamic equilibrium. So first of all, you need to make sure, firstly, it has to be reversible. You can't have a one-way reaction, okay? And then the equation must be balanced, guys. This is important. And you see when it comes to pressure that you must ensure. Oh, did I even check? My thing was not balanced, okay? I made an example and I did not balance it. Okay, so I have two A's, but now I should have 2 here. Okay, I didn't balance my equation. So actually I had 4 mole instead of 3. At least the example didn't change. But yes. So yes, number 2, equation must be balanced. Please check it that it's balanced, because that will influence, especially on the pressure side, what will happen. Okay, and then step number 3, count the amount or the number of gaseous moles on each side. That's also applicable to the pressure. What if you change pressure? And then step number 4, determine if the forward reaction is exothermic or endothermic, as well as the reverse reaction for step number 5. Okay, so that's where you're establishing, is it exothermic, endothermic? They would normally indicate with the enthalpy. If it's exothermic, the enthalpy will be less than 0. If it is endothermic, the enthalpy will be more than 0. Okay, and then step 6, the change. Okay, what kind of change actually affected your equilibrium? Is it temperature? Is it pressure? Is it the amount of the concentration? I didn't mention one thing, the catalyst. Does the catalyst have any effect? No, it doesn't. So if there's anything about the catalyst, don't bother yourself trying to figure out what will happen. It doesn't affect equilibrium. The catalyst affects the rate of the reaction. Okay, and then step number 7, decide, okay, according to Le Chatelier's principle, which reaction is favored. Firstly, you decide which is favored. Is it the forward that is favored, or is it the reverse that is favored? Okay, and then lastly, how the concentrations of the reactants and products change. So if it's forward, what will happen, what would the change be, and so forth. So basically those are the steps. I think the important ones, step 1 to 3, especially step 2, please make sure that your equation is balanced. All right, and but everything is quite important. So we're going to look at an example, and then we're going to see how to apply all of this. And I'm actually feeling a little bit warm, so I'm going to remove my flower scarf. So let's just take a break. Alrighty, welcome back. So the example we're going to look at, we have the following reactants. We have a Y2, which is a gas. Then we have 2A2X, which is a gas. So everything is, not everything is a gas, but most are gases. All the reactants are gases. And then we have BA2. All right, and then product side, we have 3A2 as well as BX2Y2, which is a solid. And then we can see that this reaction is actually exothermic. All right, so in the following cases, we're going to explain which reaction is favored and how the concentration of the product A2, the one that I've underlined in red, will change. Okay, so according to our steps, first of all, let's see. Step number 1, is it reversible? Number 2, is the equation balanced? Well, there are 2 y's. This side, there are also 2 y's on the product side. We have 4 a's plus 2 a's, so that's 6 a's. And here we also have 6 a's, so that's fine. There's 2 x's. We have 2 x's. That's good. We have 1 b on the reactant side and 1 b on the product side. So everything is balanced. Great. And then count the number of gaseous moles on each side. So I'm going to just indicate it with a different color. So the number of moles, we have 1 over here, plus 2, plus another 1. So we actually have 4 moles this side. And on the product side, we have 3 gaseous moles. We're not just counting all the moles, guys, only for the gases, okay? So we have 3 moles. Okay, perfect. Now, step number 4, determine if the forward reaction is, so yes, the forward reaction is exothermic. Okay, so I'm just going to say forward is exothermic. Okay, therefore, reverse is endothermic. Okay, so we've done that, and then the change that disturbs the equilibrium. Let's go see. For case number 1, it says the system is heated. Okay, so if it's heated, it means naturally the one that absorbs heat. Okay, that is what will be affected. Okay, so the disturbance comes on the endothermic portion. Okay, so let me go back. Let me use another color. Let me go for green. But temperature, no, let's go for red with temperature. So the system is heated, okay? So basically we're saying we are increasing temperature, all right? And what will it favor? Okay, so basically it will favor, remember what we said when we talked about temperature, that when you increase temperature, you're going to look at the endothermic, okay? It will favor the endothermic. So we need to say which reaction is favored. So it's going to be the endothermic endothermic reaction is favored. And where is endothermic? The reverse. Okay, so the reverse reaction is favored. Okay, and now we need to talk about how the concentration of the product will change. Okay, so before our answer, we said that the reverse reaction is favored. Okay, so this is what's favored. So then what will happen then to A2? What will happen? Will it increase? Will it decrease? Okay, let's just think about it. If your reverse reaction is favored, okay, it means that there will be an increase, right, on the reactant side. So therefore, your A2, which is a product, it'll actually be, it will decrease, basically. It will be decreased, yes. So in this case, A2 will decrease the product, okay? Because it's not product favored, it is reactant favored, hence A2 will decrease. Now let us look at case 2. So now the concentration of Y2 is added. Let me go with purple. Okay, so now Y2 is added. Where is Y2? Y2 is on the reactant side. So we are adding more to our reactants, okay? So think about the seesaw. Okay, you have your reactants, you have your products there, seesaw. So you are increasing the mass of the reactants. Okay, so it's going to go down like that. So if we do that, what you want to do, you want to go help out the products. Okay, so which reaction is favored, the product or the forward reaction is favored. Okay, and what will happen to A2 in this case? Well, A2, because on the product side, well, it has to increase. Okay, I hope it's making sense. And in case 3, we have A2 is removed at constant pressure and temperature. So basically, again, our seesaw, almost said phenomena, but our seesaw concept, you have your reactants, you have your products. Basically, you are removing the products. Remember, when you remove the chocolates, more chocolates come in. So if you remove the products, your reactants are going to be heavy. Okay. So where are we going? We're going to help out the products. So basically, again, it is the forward reaction is favored, or it's product favored. Okay, forward reaction, and basically A2 will increase. Okay, all right, case 4. So some of the BX2Y2, the solid, is removed at constant pressure and temperature. Guys, this is part of our products, ne? But it is a solid. So when it comes to solids as well as liquids, I don't think I mentioned this, but when it comes to solids and liquids, they don't really change equilibrium shift as such. So what will happen then? Is it forward? Is it reverse? Favored? Well, none. It doesn't affect it. And also when it comes to the yield of A2, it is unchanged. Okay, so it is neither forward or reverse favored. Okay, and when it comes to A2, the gas, it is unaffected. Okay, so it won't change. Okay, and then lastly we get to, I think, yes, case 5. Pressure on the system is increased. Okay, or alternatively we could say the volume decreased. Okay, in an exam they won't tell you that increasing pressure means volume decreases. You should know that. So for as long as the volume is decreased, I know that I'm going to look out for the number of moles that are the least. So I'm going to look on the reactant side, I'm going to look at the product side. Where are the moles the least? Okay, and that is where it is favored. So I increase pressure, I've decreased volume. Where are the number of moles that are the least? If I look at it, I have the least number of moles on the product side. So therefore, this will be a forward favored reaction. Okay, and then also what happens to A2? Basically, if it's forward, it means it's product favored. If it's product favored, it means that it will increase. Okay, so I hope that is understood. Obviously, when you ask this question in an exam, you won't just say forward and then put an arrow to show increase. You're going to write out in sentences. So you're going to say, if the pressure on the system is increased, the volume is decreased. Therefore, we're going to look at the reaction where the least amount of moles are present. Okay, so yeah, that is, you would actually say it out properly in words. So you would say Le Chatelier says, okay, so pressure is increased, the volume will be decreased, and therefore that is the shift, right? That is the change, that is the disturbance. So Le Chatelier says, I will have to favor the side with the least amount of moles. So is it the reactant side or the product side where it has the least amount of moles? And therefore you do exactly that. Okay, and when you talk about yield, in this case, A2 is a product. So we talk about yield. Will the yield be a lot or it will be little? You can then comment on that. You can use the term yield, especially if they want to know about a product. Okay, so please explain it well in full sentences. Here it is really, I'm explaining it such that you understand it. But when it comes to writing it down, do the things that will get you the marks. Okay. All right, now we're gonna go on to this topic called the common ion effect. So there's this topic called the common ion effect. Okay, Basically what it says is when you have a solution, or when a solution is added to a reaction system, so you already have your reactants, you have your products and stuff, but now you start adding a solution to that. You need to identify the common ion in the solution. So okay, we'll look at examples as we go through. But if you already have a reaction that contains chloride ions, maybe you have sodium chloride, for example, okay, and then you add hydrochloric acid, so you would see that the common ion there is actually the chloride ions. Okay, so you had your aqueous sodium chloride, okay, maybe it is diluted, or it's in a concentration form. So yes, it's there in aqueous form, okay, in the aqueous phase. So you are adding now an acid called hydrochloric acid. So your common ion, like I said, it would be the chloride ions. Okay, so you need to identify the common ion and then explain the effect of the common ion on the chemical equilibrium. So you're going to have to, still using Le Chatelier, you'll see what will happen if I add hydrochloric acid to the sodium chloride solution. What will happen, So here, again, I got a table from Mind the Gap study guide that is freely available on the internet, provided by the government. So here it just tells you what basically you can expect. So let's say you have hydrochloric acid, okay, and you are adding hydrochloric acid to an equilibrium mixture, okay. So what will that do? It basically increases the hydrogen ion concentration, or you would say the hydronium ions, okay. It also increases the chloride ion concentration, but it decreases the hydroxyl ion concentration. So if you're looking, that is what basically would happen this is like in general, if you were to add hydrochloric acid. If you were to add sulfuric acid as well, it would increase the hydrogen ions, or the hydronium ions, okay. It would increase the sulfate ion concentration, but decrease the hydroxyl ion, and it will decrease it because you're adding an acid. So if you're adding an acid, it will decrease the pH, right? So your base basically would decrease. Hence, in both examples, we see that the hydroxyl ion is actually decreasing. But now what if you add a concentrated sulfuric acid? So that is in liquid form. Well, basically that would extract water from the system. Okay, and that is why in your topic of organic chemistry, when you look at the organic reactions, you would have a catalyst such as concentrated sulfuric acid, and this is the effect that it has. It basically dehydrates. So if you have concentrated sulfuric acid in liquid form, it dehydrates or extracts water from the system. Okay, and you'd also see in some in some organic reactions, you also have sodium hydroxide. They would either say diluted sodium hydroxide or concentrated sodium hydroxide. And what effect does that have? So basically, if you're going to add to the solution a base like sodium hydroxide or potassium hydroxide, it increases the hydroxyl ion concentration. Okay, so a solution containing chloride ions, for example in sodium chloride, it'll increase the chloride ion concentration, and it will decrease the silver ion concentration in a solution. Okay, so basically here, if you have some silver ions in the solution and you keep adding, maybe you add sodium chloride to it. Remember, chlorine and silver actually form a precipitate. So while the chloride ions are increasing, the concentration is increasing, actually the silver ion concentration in a solution will decrease. Okay, so yeah, that's basically that. If it doesn't make sense, we're going to do an example and you'll see how to apply all of this. And here's the example. So let's say for one, you have cobalt, so CO is cobalt, or cobalt chloride, okay, in aqueous solution, and then we have water as well, 6 moles of water. Then we have, what is it? Cobalt water? Just kidding. But yes, these are our products, as well as the chloride ions. Okay, so the color of the reactants is blue. And while the reaction is ongoing, you have a purple pink color. And then when your when your products have formed, then you have pink. And this reaction is actually exothermic, so it releases heat to the environment or to the system. So here with me with the example we're going to look at, basically you have five samples of this purple pink solution. Okay, and I want to know, or what we should actually figure out is, what if there are certain changes that are made to these five samples? What answer are we expecting? What is the common ion, and what is the effect of that common ion? Okay, so let's look here. So in the first case, we are removing heat, or rather we are cooling this this purple pink solution. Okay, so what would happen if you decrease the temperature or you are cooling? What happens in case number 2 if you add more water? You are diluting it. What would happen in case number 3 if you add sodium chloride? Okay, what would happen in case number 4 if you add sulfuric acid, which is concentrated? Remember what concentrated sulfuric acid does? It dehydrates. What would happen if in case number 5 you add silver nitrate to the solution? Okay, so yeah, we are gonna discuss that briefly. Alright, so what would happen if we decrease temperature, okay, or we cool it down? Already this reaction is an exothermic reaction, okay, meaning it is forward favored or product favored. Okay, yeah, product favored. So I would expect, first of all, my solution to turn pink. Okay, so here basically it would turn pink over here. Okay, yeah. And then what happens if we add water? Okay, let's go see, where is water? There's not an ion though, but we want to see what is common. Where is the water at? Okay, so the water is on the reactant side. Okay, so if you're going to increase, yeah, okay, remember that example that we talked about, and I said that solids and liquids don't affect equilibrium? Okay, I actually just meant to say solids in particular because the change in mass is not that significant. But in this case, if you add water, so you are sort of like diluting it, that will make a difference. Okay, the color will somewhat change, and we need to then see what will the color be. Okay, so if we add water, the water is on the reactant side. Okay, so we're basically, according to Le Chatelier, we're increasing. Okay, we are increasing our reactants. Okay, so what shift would they be? If you're gonna increase reactants, according to Le Chatelier, you're gonna move all the way to the product side, so it'll be forward favored, okay, or product favored. So again, by adding water, your solution will be pink. Okay, yeah, I have so much space. I basically put that lot of space because I was gonna explain all of this. Thought I was gonna write all of this down by saying according to Le Chatelier, da 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 da. But we're never gonna finish if I write everything down. Okay, so let me just remove that. All right, let's go back. Now we are adding sodium chloride. Okay, so we're adding sodium chloride and want to see what would be the common ion here. So it's going to be the chloride ions. Okay, we have chloride ions over here on the product side. So we're basically increasing the products. Okay, so what would happen if you increase the concentration of the products? Well, Le Chatelier says, okay, if you're increasing on the product side, we're going to have to do something on the reactant side, okay, just to balance things up. So your reaction will actually be reverse favored. Okay, it will favor the reactants. Okay, so it will turn blue, basically, by adding sodium chloride. okay, because chloride ions are the common ion, okay, and that's the effect that it actually has. Okay, now we're going to look at, we are adding concentrated sulfuric acid. So what did we say about concentrated sulfuric acid? It basically causes some dehydration. So what are we doing then? We are taking away the water. Okay, we are dehydrating it. And if you're going to take away from the reactants, what does the Chatelier say? Like, if you're going to take away, we're going to add to it, because it's unfair that you are taking away from them. Let's just compensate by adding. So it will be reactant favored, okay? Yes, reactant favored or reverse favored. So it will turn blue. Okay, I hope all of this is making sense. And then lastly, what if we add silver nitrate? Okay, so if you add silver nitrate, first of all, it won't really affect it on the reactant side, but the product, guys, if you're adding silver nitrate, the silver ions and the chloride ions will come together and they will form a precipitate. Okay. So I hope you understand that so far. So like I said, by adding silver ions, by adding silver ions, your chloride ions will come into contact with the silver ions. A precipitate will form. So you're basically taking away the chlorine ions or the chloride ions in the solution. They will decrease. Why? This precipitate is busy forming at the bottom. Okay, so in this case here, I'm going to indicate the the precipitate silver, what do you call it? Silver chloride. So let's just say silver chloride, making it green, is forming there. Okay, by it forming, you have less chlorine or chloride ions. Okay, so you have less, let me put it this way, you have less chloride ions. So if you look at your reaction there, if you take away, so it's a product, right? The chlorine is on the product side, or the chloride ions are on the product side. So if you keep taking away from the products, what does Le Chatelier suggest you do or tell you to do? Well, basically, you're going to be product favored, because if you're taking away, we need to replace it. Okay, so again, your solution would be pink. Okay, just write it in green. It will be pink. Okay, and that is how you would answer that. That is basically the common ion effect. Okay, I hope it makes sense. I hope you know what's going on, but I hope this example as well assisted in understanding. All right, and now we're going to come to the equilibrium constant. Okay, so we have made a video on the equilibrium constant. Okay, so we've done an example there. My husband did it, so I'm not going to do an example here, but I'll just cover the basic theory. So yeah, the equilibrium constant, Kc, that's basically concentrations at equilibrium of solutions and gases. Okay, so basically when I say solutions, I mean AQ, aqueous solutions, and gases. Okay, in a closed system in dynamic equilibrium. So important thing to always remember with chemical equilibrium or equilibrium, closed system, closed system in dynamic equilibrium. Okay, and then when we calculate this constant, we are looking at solutions as well as gases. Your solids and your liquids, well, they have a concentration of 1, which doesn't really make a difference in our calculation, so we don't consider them. But your gases and your solutions, they have a certain concentration at equilibrium. An important thing is at equilibrium. You don't just take the concentration initially or during a change. No, we're looking at, basically at equilibrium. Okay, and like I said, solids and pure liquids are excluded from this Kc constant. Okay, and because it's a constant, this Kc expression, we do not have units. So I have an example here. So let's say these are your reactants here. 2P, it's a gas. We have 3R, that's a solid. And then our products, 2S, which is a solution, as well as 4T, which is a solution. So if you were told to calculate the Kc constant. Okay, basically you would take the concentrations at equilibrium of the products, okay, and for each term or expression over there, its coefficient, the number that's next to it, its coefficient, you will put it in the exponent. It'll be your exponent. Okay, so yeah, if you're calculating the Kc constant, you're basically taking the concentration of the products at equilibrium, all right, and you're basing it basically to the power of your coefficient all over the concentrations of your reactants at equilibrium, also to the power of the what do you call this now? Yes, the number next to it, the coefficient. Terminology. Okay, let me change this color now to blue. So in this case, if we were to calculate Kc, what would we do? So we're going to take the products over concentration. So we're going to assume this is the concentration at equilibrium. So you would take T, the concentration of T. So the square brackets indicate concentration. Okay, concentration of T at equilibrium. And then the coefficient becomes the exponent. So to the power 4. Okay, and obviously what will take part in this Kc expression, it is S, it is T, it is P, but not R, because R is a solid. Okay, so we have T to the power 4, and then the concentration of S at equilibrium to the power 2 all over the concentration of P at equilibrium to the power 2. That is basically what you would do, and you would use the Rice method that my husband spoke about to basically get the concentrations at equilibrium depending on the information that they have given you. Alright, so now let's talk about factors that influence this Kc expression, okay, this constant. Basically, we always refer to like pressure, concentration, temperature, a catalyst. Okay, so yeah, but in this case, for the Kc expression, for your equilibrium constant, the only thing that has an effect on it is temperature. Temperature is the one that influences how high or how low this constant is. Okay, so if you were to talk about pressure or concentration or a catalyst, they don't have an effect. Okay, so especially this is good for your multiple choice section. They like tricking you out, or yeah, checking that you know your theory. So don't be tricked. Only temperature has an effect. So now what happens if we change the temperature of a closed equilibrium system? Basically, if it favors the forward reaction, whether it is endothermic, exothermic, doesn't matter, but if it favors the forward reaction, remember the forward reaction is where we are forming the products. Okay, so basically there'll be an increase in your products, all right, and your reactants will decrease. All right, and because remember the Kc constant, we said that it is the concentration of your products over the concentration of your reactants at equilibrium. Okay, can't remember if it's M or N. But basically, if your products, if this value, if your numerator increases, your numerator is directly proportional to this Kc expression. So if your products increase, then it only makes sense for your constant to also increase. Okay, so yeah. On the other hand, if when you change the temperature of a closed equilibrium system and then the reverse reaction is favored, what will happen? Basically, the reverse is all the way to your reactants. Okay, so you will have an increase in reactants, your products will therefore decrease. So if you were to increase your your reactants there, if you were to increase your denominator, the value of your Kc will definitely decrease, because the higher your value is in the denominator, then the lower the Kc value becomes. So that is why you have a lower Kc. Okay, so please just remember that, especially when you answer questions, when they ask you what effect a certain change in temperature will have on your equilibrium constant. And another thing, so if you have a low value for your equilibrium constant, basically if you have a value smaller than 1, where you now have your exponents that are negative, so maybe you'll have like 1 times 10 to the power negative 2. Okay, so that's what I mean by your exponents being negative. Basically, if it's quite low, it means now we're getting back to the term yield. It means that your product yield is low. Okay, so if you are hoping to produce a certain thing and you see that, okay, my KC value is actually less than 1, please don't continue with this. You're not going to get a lot of product, meaning you're not going to sell much. Okay, so basically the product yield will be low and the industrial process will not be economically viable. Okay, so for those who like asking, like, why am I learning all of this? Well, if you're planning to be an industrial engineer, this comes into play. All right, cool. If then your equilibrium constant is higher than 1, then that basically means that your product yield is high. Okay, so in this case, your industrial process may be economically viable and you can go ahead with it. But that isn't the only thing that determines economically whether something is economically viable or not. There are more factors to it, but where we are right now with the equilibrium constant, this will be fine. Okay, so like I said there, you can check out our video for an example or application. Okay, so the video is called Chemical Equilibrium, and we have that straight line, I don't know what it's called, and then equilibrium constant calcs. All right, so yeah, now next we're going to be talking about interpreting the dynamic equilibrium graphs. You know those graphs where you see something, it's like flat, and then all of a sudden there's a increase, and then there's a gradual increase, and yes, we're going to talk about that next. All right, so lastly, we're going to look at the interpretation of dynamic equilibrium graphs. Okay, so we have to, from what we've learned about Le Chatelier and disturbances and equilibrium, we need to now look at the graphs, see how we can interpret them and how we can understand the theory we've read, how we can actually plot it in a graph or understand the graph and interpret it theoretically. So yeah, there are graphs that you can use to represent dynamic equilibrium. For one, you can use the reaction rate versus time graph. You can use the number of moles versus time, the mass versus time, or the volume versus time. And you can also use concentration versus time. So what we're going to focus on now is the reaction rate versus time, the number of moles versus time, as well as the concentration versus time. Okay, and then I have an example here of sulfur dioxide plus oxygen giving us sulfur trioxide. Okay, and as you can see here, the reaction is exothermic. All right, so we're going to look at the 3 types of graphs that I told you about and then see if we apply maybe a change in temperature, a change in concentration, a change in pressure, as well as a catalyst, what will happen. Okay, so I've just considered the cases where I add temperature, I add pressure, I add the concentration, particularly the concentration of oxygen, and I also add a catalyst. Okay, so if I add temperature and the graph looks a certain way, if I were to not add temperature, if I were to heat up the system and a graph looks a certain way, well, if I cool the system, the graph will just do the opposite. Okay, basically it will rotate, or not really rotate, it would reflect about the dependent variable. Because no, let me not say the dependent variable, but basically if I have a sharp increase like this because of an increase in concentration and it goes like this, well, if I have an imaginary line there, let's not say anything about dependent variables or independent. Okay, so if I increase concentration and it increases sharply and it reduces over time because of Le Chatelier, well, if I were to decrease, it would do this and come this way. That's what I mean about the opposite will happen. So it's like a reflection, but not about any axis. Let me not lie. Okay, so let's have a look at the graphs. So I decided I'm just going to draw them beforehand. I did a recording where I was drawing them as I spoke, but it took a very long time. So I decided, let me just draw it separately. So we have reaction rate versus time. We have number of moles versus time. And we have concentration versus time. And as you can see here, I keep varying something. There's initial conditions and then increase in temperature, increase of the concentration of oxygen, increase in pressure, as well as the addition of a catalyst. Okay, so let's have a look then what happens with the reaction rate versus time. So initially, for the forward reaction, by the way, the forward reaction is exothermic, right? So let me just indicate it. So the forward reaction is exothermic and the reverse reaction is endothermic. So initially, the reactants, which forward, the rate of reaction will decrease with time. Why? Because your products are being formed. So with the products, your rate will increase, okay? But because we have dynamic equilibrium, do you see that the rate of the forward eventually equals the rate of the reverse, okay? And in this period over here, that is where equilibrium has been reached. All right, if we look at the number of moles versus time, well, the number of moles versus time looks exactly like the concentration versus time until we get to pressure. So we'll see. So with the number of moles versus time, again, initially, the reactants have the highest number of moles, okay? But because products are being formed, products increase with time, number of moles, as well as the concentration increases over time with the products, but the reactants, they decrease over time. Okay, but you still have a lot of number of moles for your reactants versus your products, okay? Because ultimately, if you look at the number of moles here, for your reactants, we have 3, okay? 2 plus 1, and then for your products, we have 2. So it'll always be lower, okay? So, yes, and then until we reach a point of equilibrium, okay? I tried to make the lines parallel, but it's not so easy sketching. Alright, so, but yeah, basically, where you reach equilibrium, that's where you have a horizontal line. Now, what happens when we increase temperature? Guys, when we increase temperature for an exothermic reaction, well, basically, if your forward reaction is exothermic and you increase temperature, what happens is the system becomes heated up, but your endothermic reaction becomes favored always when you heat up your system. When you cool down your system, exothermic is favored. So because we know that endothermic is the reverse reaction, here we see our reverse increasing significantly. The rate of reaction increases significantly. But the rate of reaction for our forward reaction, well, it will increase slightly because of that added heat, okay? But over time, it increases gradually because, like we said, the rate of the forward reaction should equal to the rate of the reverse reaction. So the reverse reaction, it had that boost, with the increase of temperature, but now it needs to calm down. So over time, the rate decreases. And then your forward reaction, it increased slightly, but over time, it also increased, okay, gradually, until again you get to a point of equilibrium where the both of them are equal, because the rate of the forward is equal to the rate of the reverse for dynamic equilibrium. Please don't forget that. What happens to the number of moles? Okay, like we said, your forward reaction is exothermic, meaning your reverse reaction is endothermic. Okay, so basically, your concentration or your number of moles, when it comes to reactants, because the reverse reaction favors it's like reactant favored, your reactants should actually increase, and that is why you see an increase there for oxygen as well as sulfur dioxide, and a decrease in your sulfur trioxide, okay, for both the number of moles as well as your concentration, okay, until we get to a point of equilibrium where now they are parallel, okay, so they're just quite horizontal. All right, So that's basically what happens there. Yeah? I hope you're following. Now what happens if I were to increase the concentration of oxygen? So oxygen is on the reactant side. Okay, so when you increase the reactants, remember the seesaw? So your reactants are going to be more heavier than your products. And what does Le Chatelier say? It says we must now go over to the products and help them out. So in this case, we are going to see a rate of reaction. Okay, for the rate of reaction graph, when you increase concentration, there will be an increase, okay, a sharp increase for both the reverse and the forward, okay. But ultimately, your forward reaction will have a sharp increase and then calm down, okay, whereas your reverse reaction will have a gradual increase until they both reach equilibrium where they are equal. Okay, rate of the reverse is equal to the rate of the forward for dynamic equilibrium. I'll keep on repeating this. And here, in terms of number of moles as well as concentration, the graph is still the same, right? So, because you increased the number of moles or the concentration of oxygen, it will have an initial increase, all right? It will have a jump there. I hope you see it with this gray, okay? It will have a sharp increase because you just increase the number of the concentration, so the number of moles will increase. Remember our formula here, C is equal to N over V. So the number of moles is directly proportional to concentration. All right, so you will see a sharp increase for oxygen, okay? But ultimately, because Le Chatelier says what will oppose, that's if we reduce the reactants and increase the products. So we see over time, gradually, your product, sulfur trioxide, it actually increases, whereas your reactants start decreasing because Le Chatelier is at place. And then we reach again a point of equilibrium. And the same happens for the concentration. Okay, and then now we get to pressure. Again, if you look at the rates of reaction, what actually influences it, you'll see also the increase in pressure will increase the rate. Okay, so there's a sharp one for the forward and a gradual increase for your reverse. But ultimately, again, they reach equilibrium where they are both equal. The rate of the forward being equal to the rate of the reverse reaction. Okay, what happens now to the number of moles? Well, if you were to increase pressure, okay, think about it. We said if you increase pressure, you are decreasing volume, okay? If you are decreasing volume, what happens to your number of moles? Well, we're going to have a look at the equation, okay? We're going to look at the least amount. Increase in pressure, you look at the least amount of moles. We have 3 moles here on the reactant side, and we have 2 on the product side. So the forward reaction will be favored. So your product will increase. We're expecting the product to increase, and we can see that with the number of moles, they are increasing, okay? And your reactants will decrease, okay, because they are not favored until we reach a point of equilibrium, okay? So we reach a point of equilibrium. And then what happens to the concentration? Guys, when you increase pressure, remember pressure is applicable for gases, right? So when you increase pressure for your concentration, all, and I mean all, will have an initial sharp increase. So all your reactants as well as your products will have an initial sharp increase, okay? But your products, again, because it is forward favored, product favored, your products will continue with that gradual increase until it reaches equilibrium, whereas your reactants will go on decreasing slightly or gradually until it reaches equilibrium. Okay, so we reach equilibrium over here. Okay. Another thing with the pressure, why is it that the number of moles versus the concentration is actually different? The graphs, again, looking at our equation, C is equal to N over V, we have increased pressure, okay? An increase in pressure means that our volume has decreased. If your volume has decreased, do you see here? volume and concentration are inversely proportional. So if your volume decreases, it means your concentration will increase all around. So that is why for your reactants and your products, you have that sharp increase. But because the reaction is forward favored or product favored, your products will continue increasing gradually, whereas your reactants will decrease gradually until equilibrium is reached. Lastly, what happens when you add a catalyst? For your rate of reaction, remember the catalyst, it actually lowers your activation energy, okay, such that eventually with effective collision, you're going to get an increase in the rate of reaction, okay. But now, what the catalyst does, it's actually to the benefit of both your forward and your reverse reaction. So it will all basically they're touching each other there, so they basically will have the same rate. Okay, I hope you get it. They'll have the same rate of reaction when it comes to your rate of reaction versus time graph. So both your forward and your reverse reactions will have the same rate of reaction when a catalyst is added, because when it's added, it's not like it's favoring the reactants or favoring the products. It favors both. It favors the whole system. So that is it with the reaction rate versus time graph. What happens then for the number of moles versus time graph, as well as the concentration versus time? Well, basically, like we said, with a catalyst, equilibrium is not really, a catalyst doesn't really affect equilibrium. Okay, so when you add a catalyst, even with the number of moles, it doesn't change the number of moles. They're still the same. Okay, you just affected the rate of reaction. You don't affect the number of moles, nor do you affect the concentration. Okay, catalyst has nothing to do with that. So that's basically how you would interpret these graphs. Okay, we're gonna do an example so that you see practically what kind of questions do they ask. But honestly, if you get this, you're good to go. Okay, but yeah, let's look at an example and then we'll finish off the session. Alright, so just to finalize our session, we're going to look at a question from Mind the Gap. I wanted to look for one in an exam, but it was going to take, again, forever. So I think this is a very good example. So let's see. It says a fertilizer company produces ammonia on a large scale at a temperature of 450 degrees Celsius. The balanced equation below represents the reaction that takes place in a sealed container. Okay, so we see that nitrogen and hydrogen give you ammonia, and the equation is actually, or rather the chemical reaction is exothermic. All right, so to meet an increased demand for fertilizer, the management of the company instructs their engineer to make the necessary adjustments to increase the yield of ammonia. In a trial run on a small scale in the lab, the engineer makes adjustments to the temperature, pressure, and concentration of the equilibrium mixture. The graphs below represent the results obtained. Okay, so if we just look at the graph, just scrutinize it, we see we have nitrogen. Okay, let me just make some notes. Okay, what happened? All right, it's fine. But anyway, we see that we have nitrogen, which is the solid line, and then we have hydrogen, which is the dotted line, and then NH3, which is the dashed line. Okay, so initially they're all at equilibrium, I would suppose, and then T1, something happens. Okay, there is an increase, I don't know if you can see, but there's an increase of concentration of nitrogen. Okay, yes, because it's a concentration versus time graph. So the concentration increased, all right? And as a result, what does Le Chatelier say? Well, if you increase the reactants, or one of the reactants, to counteract it would have to, It would have to be product favored, right? Or forward reaction favored, or forward favored, okay? So now, in that case, we would have more products, so which is what we want. So the engineer did well by increasing nitrogen. Okay, so we see that nitrogen increases, all right, and but it is a sharp increase. First of all, whenever you have a sharp increase, it could either be concentration or pressure. With temperature, there's always a gradual increase or decrease. Okay, so they increased the concentration of nitrogen, and then as a result, because of Le Chatelier, it's going to be product favored. You're going to have a gradual increase in ammonia and a decrease gradually of the reactants, nitrogen and hydrogen. What happened at T2? Everything has a sharp increase. Okay, so remember what differed between the number of moles versus time, as well as the concentration versus time graph, is when it came to pressure. Okay, with concentration versus time, when you increase the pressure, again, remember C is equal to N over V. The higher the pressure, the lower your volume. Therefore, the higher your concentration. So we do see an increase in concentration for all, for the reactants as well as the product. Okay, so T2, there was an increase in pressure. And then T3, I see gradual increases and gradual decreases, so there must be something to do with temperature. So because it is exothermic, the forward reaction is exothermic. The reverse is endothermic. If we increase temperature, it will favor the reactants. So we should see an increase in nitrogen as well as hydrogen. If the temperature was cooled, if the system was cooled, meaning the temperature was decreased, it would favor the forward reaction. Therefore, ammonia would have to increase. So what happened here? I see that ammonia, which is the dashed line, decreases, but your reactants, nitrogen as well as hydrogen, they are increased. Okay, so yeah, in that case, it would be endothermic. So there was an increase in temperature. All right, so after having scrutinized all of that, let us answer the questions. We should flow, I believe. Okay, so question one. So it says identify the changes made to the equilibrium mixture at each of the following times. So like we said, 1.1. So T1 is an indication of an increase in concentration. T2 is an indication of increase in pressure. And T3 is an indication of an increase in temperature. Okay, because it's endothermic. All right, so now moving on to question 2. So it says, at which of the above times that the change made to the reaction mixture lead to a higher yield of ammonia? So we can see ammonia increased when the concentration of nitrogen was increased at T1, right? Ammonia also increased when the pressure was increased. It only decreased when the temperature was increased. Okay, so we would have then T1 and T2. That is when we saw a higher yield of ammonia. Okay, and then question 3, it says the engineer, let me just take this page up. So these questions are going by quite quickly, which is good. The engineer now injects 5 mole of nitrogen, 5 mole of hydrogen into a 5 cubic decimeter sealed empty container. Equilibrium is reached at 450 degrees. Okay. Now, upon analysis of the equilibrium mixture, he finds that the mass of ammonia is 20,4 grams. Calculate the value of the equilibrium constant at 450 degrees Celsius. So let us remind ourselves again, what is the equilibrium constant? Well, it is the concentration at equilibrium of the products over the concentration at equilibrium of the reactants. And the condition is that we must have gas or solutions. Okay, we can't have solids and liquids in that constant. So here we only have gases. So basically the products there, we're going to have the concentration at equilibrium for ammonia, okay, to the power 2, and then we're going to have the concentration of nitrogen times the concentration of hydrogen at equilibrium to the power 3. So we need to then use the Rice method to actually get what the concentrations are at equilibrium. Currently, we have the initial number of moles. Okay, so I'm just going to draw the table quickly and then we'll fill it up and then be done. Alright, so I've drawn the table and then I've listed here. So we have 1 mole of nitrogen, 3 moles of hydrogen, and 2 moles of ammonia. It's the balanced equation that was given to us. Here I have a double line just to indicate that these are your reactants over here. And after the double line, you have your products. Okay, so the ratio, so R stands for ratio. We have 1 mole here, so it's 1 is to 3 is to 2. That is basically our ratio of our reactants as well as the product. Now, initially, they told us that this engineer, he injects 5 moles of nitrogen. Okay, so we have 5 moles of nitrogen initially. We also have 5 moles of hydrogen. Okay, and you know, initially we don't have any products, so you always have 0 here. Okay, if you're starting off this from scratch, there aren't any products yet. Okay, so it's 0. Now, what is the change? So C in Rice stands for change. Okay, so what we were told is that upon analysis of the equilibrium mixture, he finds that the mass of ammonia, our product, is 20,4 grams. So at equilibrium, we already know what our mass is. So we need to back calculate to get the number of moles. Okay, so remember the equation. Let me just do it at the bottom. The equation here that says that the number of moles is the mass over the molar mass. Now I need to check on the periodic table. So we have nitrogen, we have 3 times hydrogen. Hydrogen, I already know that it has 1 gram per mole. So if I multiply by 3, it will be 3 grams per mole. Okay, that's the molar mass. And then nitrogen, I believe it is 14. Okay, so you get to know these things when you practice a lot or when you do a lot of these questions. So ultimately the molar mass, the total molar mass would then be 14 plus 3, which is 17 grams per mole. Okay, so they gave us the mass. They said it's 20,4 grams. And then we have the molar mass, which is 17 grams per mole. So we need to get the calculator. Jeez, I always forget to get the calculator. Yeah, there's the calculator. So we had 20,4 divided by 17. Okay, so let's just do this quickly. As we wait. Okay, I actually forgot to load the calculator before starting this question, so apologies for that. Please forgive me for taking up time. Okay, so yeah, we have 20,4, right, divided by 17, and that is 1,2. Okay, so we have 1,2 mole at equilibrium for, what do we have there? For ammonia. So at equilibrium, we have 1,2 mole. Okay, remember your reactants are actually decreasing while your products are increasing. So what would I have to add to 0 to get 1,2? I'm definitely going to need 1,2. But remember now, we have these, the ratio 1 is to 3 is to 2. Okay, so if we're going to now look at what we have for the 2, we have, I just want to use a different colored pen. Okay, so for 2 we actually have 1 comma 2. Okay, so meaning if I were to divide that by 2 to get the 1, it would be 0 comma 6, and if I was to multiply that by 3, I would get 1 comma 8. So this is how it would relate. Okay, so we can write those down. That would be the change. Okay, this is me dealing with the change. So I'm gonna have 0 comma 6 over here, and then I'm gonna have 1 comma 8. So my reactants keep decreasing, so 5 minus 0 comma 6, that will be 4 comma 4. So that's equilibrium at sorry, that is the number of moles at equilibrium. If I have 5 minus 1 comma 8, okay, 5 minus 2 is 3, so that's going to be 3 comma 2, right? Yes. Cool. Now we can calculate equilibrium. Okay, we calculated it with moles. Now we're going to need to calculate it now concentration. Okay, they gave us the volume. They said it is 5 cubic decimeters. So basically concentration is equal to number of moles over volume. Okay, so my concentration is going to be equal to number of moles, 4 comma 4 over volume, which is 5. Here we're going to have 3 comma 2 over 5, and we're going to have 1 comma 2 over 5. So that's basically, yeah, so what is 4 comma 4 divided by 5? Well, that's 0 comma 88. Okay, at least we're not dealing with a lot of numbers. If I say 0 comma 2, 3 comma 2 divided by 5, that's 0 comma 64. I could have used ratios, but we have it, so it's all good. And then 1 comma 2 divided by 5, which is 0 comma 24. Okay, so yeah, now we can get back to our equation here. We can just copy it over and then put in the missing values, and then we can get our equilibrium constant. And then we are done. We are done, guys. Thank you for bearing with me and the technical challenges and the blocked nose. and so we have 0 comma 24. All of it is squared. Okay, our nitrogen, we have 0 comma 88. Oh no, the battery. Wow. Okay, and then for the hydrogen, we have 0 comma 64, and that is to the power 3. Okay, so if we calculate that quickly, we are going to get 0 comma 24 squared divided by 0 comma 88 times 0 comma 64 cubed. And our answer, our equilibrium constant, so that is 0 comma 25. Yes, 0 comma 25, which is less than 1. Right? And if that's the case, is it economically viable? No, you're not getting much of your product. We want a value higher than 1 to know that, you know what, we're going to get a lot of our product here. So yeah, that's what we can conclude. But they didn't even ask us that. They just said we must calculate the equilibrium constant at 450 degrees. Okay, so they would have to actually lower this temperature. Maybe they can get better results. Yeah, but at the end we want our equilibrium constant to be higher than 1 so that we can get a higher yield of ammonia, and this could be economically viable. Okay, thank you for tuning in. Enjoy the rest of your day.